Imagine a world where the very fabric of reality, everything we see and touch, is composed not of solid particles, but of tiny vibrating strings. These strings are not just theoretical constructs, but are believed to be the fundamental building blocks of the universe. They are so small that they are beyond the reach of our most powerful microscopes, yet their vibrations create the very essence of matter and energy. This is the captivating premise of string theory, a revolutionary idea that attempts to rewrite the fundamental laws of physics. It suggests that at the most microscopic level, the universe is a symphony of vibrating strings, each with its own unique frequency. These frequencies determine the properties of particles, much like how different musical notes are produced by varying the tension and length of a string on a musical instrument. Like the strings of a cello or a violin, these minuscule strands of energy vibrate, dance and interact, their harmonious symphony giving birth to the universe and everything within it. The vibrations of these strings are not random. They follow precise mathematical patterns, creating a cosmic melody that underlies the structure of all matter and forces. For centuries, physicists have grappled with the universe's deepest secrets, seeking to understand the fundamental building blocks of matter and the forces that govern their interactions. From the ancient Greeks, who first pondered the nature of atoms, to the modern scientists working with particle accelerators, the quest to understand the universe has been a journey of discovery and wonder. While the standard model of particle physics has successfully explained many phenomena, it falls short in explaining gravity's true nature and its relationship to the other fundamental forces. The standard model has been a powerful tool, but it is incomplete, leaving many questions unanswered and many mysteries unsolved. Here, string theory steps onto the cosmic stage, offering a bold and elegant solution to this long-standing puzzle. By proposing that gravity is also a result of string vibrations, it provides a unified framework that could potentially explain all the forces of nature in a single, coherent theory. Instead of point-like particles, string theory proposes that everything in the universe is made up of one-dimensional vibrating strings. These strings can stretch, twist and loop, creating a rich tapestry of interactions that give rise to the particles and forces we observe. Just as a violin string can produce a variety of notes depending on its vibration, these fundamental strings vibrate at different frequencies, giving rise to the diverse array of particles we observe. Each type of particle, from the electron to the quark, corresponds to a different vibrational mode of these strings. This simple yet profound shift in perspective has the potential to unify all the forces of nature, including gravity, into a single harmonious framework. By viewing the universe as a symphony of vibrating strings, we may finally be able to understand the underlying unity of the cosmos and the elegant simplicity that governs its complex behavior. To understand the essence of string theory, we must journey deep into the heart of matter, far beyond the realm of atoms and quarks. This journey takes us to a realm where the very fabric of reality is woven from the tiniest threads of energy. These threads, or strings, are the fundamental constituents of everything in the universe. They are the building blocks that form the foundation of all matter and forces. Here, we encounter the fundamental building blocks of string theory, minuscule, one-dimensional strings. These strings are not like the particles we are familiar with, such as electrons or protons. Instead, they are incredibly tiny loops or segments of energy that vibrate at specific frequencies. These strings are so incredibly small that if an atom were enlarged to the size of our solar system, a single string would be no larger than a tree on Earth. This comparison helps us grasp just how minuscule these strings are, existing at a scale far beyond our everyday experience. But despite their infinitesimal size, these vibrating strings hold the key to understanding the universe's grand design. The way these strings vibrate and interact with each other determines the properties of all particles and forces in the universe. It's as if the universe is a grand symphony, with each string playing a unique note that contributes to the overall harmony. Like the strings of a musical instrument, the vibrations of these fundamental strings determine their properties. Just as a guitar string can produce different notes depending on how it is plucked, these tiny strings can produce different particles depending on their vibrational patterns. Different vibrational patterns correspond to different particles, just as different notes emerge from a guitar string depending on how it is plucked. For instance, a string vibrating in one way might correspond to an electron, while a string vibrating in another way might correspond to a quark. Imagine a single string vibrating at a particular frequency. This specific vibration pattern gives rise to a particular type of particle with its own unique properties and characteristics. This vibration might correspond to an electron, a fundamental particle carrying a negative charge. Electrons are essential components of atoms, playing a crucial role in chemical reactions and the formation of molecules. Another string vibrating at a different frequency might represent a quark, the building block of protons and neutrons. Quarks combine in various ways to form the protons and neutrons that make up the nuclei of atoms. In this way, the entire universe, with its dazzling diversity of particles and forces, emerges from the intricate symphony of vibrating strings. Each string, with its unique vibrational pattern, contributes to the rich tapestry of the cosmos, creating everything from the smallest subatomic particles to the largest galaxies. String theory's allure extends far beyond its elegant simplicity. It captivates the imagination of physicists and enthusiasts alike, offering a glimpse into the fundamental nature of reality. At its core, string theory proposes that the most basic building blocks of the universe are not point-like particles, but rather tiny vibrating strings of energy. These strings can vibrate at different frequencies, and their vibrations determine the properties of the particles they form. This elegant idea has the potential to unify all the forces of nature into a single coherent framework. It offers a compelling solution to some of the most profound mysteries in modern physics. For decades, scientists have been grappling with the challenge of reconciling two seemingly incompatible theories: Einstein's theory of general relativity and quantum mechanics. These two pillars of modern physics describe the universe in fundamentally different ways, and finding a way to bring them together has been one of the most significant quests in the field. One of the most significant challenges lies in reconciling Einstein's theory of general relativity, which governs the universe on a grand scale, with quantum mechanics, the strange and counterintuitive world of the very small. General relativity provides a beautiful and accurate description of how gravity works, explaining phenomena such as the bending of light around massive objects and the expansion of the universe. However, when we try to apply the principles of quantum mechanics to the gravitational field, we encounter mathematical inconsistencies and paradoxes. General relativity describes gravity as the curvature of space-time caused by massive objects. Imagine space-time as a flexible fabric that can be stretched and warped by the presence of mass. This curvature affects the motion of objects, causing them to follow curved paths rather than straight lines. This theory has been confirmed by numerous experiments and observations, such as the precise measurements of the orbits of planets and the detection of gravitational waves. Quantum mechanics, on the other hand, describes the universe in terms of probabilities and uncertainties. It reveals a world where particles can exist in multiple states at once, and their properties are not determined until they are measured. This probabilistic nature of quantum mechanics has been confirmed by countless experiments, such as the famous double-slit experiment, which demonstrates the wave-particle duality of light and matter. These two fundamental theories, while successful in their respective domains, seem fundamentally incompatible, leading to contradictions and paradoxes when applied together. For example, when we try to describe the behavior of particles in the presence of strong gravitational fields, such as near a black hole, the equations of general relativity and quantum mechanics produce nonsensical results. This has led physicists to search for a more fundamental theory that can encompass both. String theory offers a way to bridge this gap. By proposing that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings, it provides a framework that can incorporate both general relativity and quantum mechanics. These strings can stretch, merge and split, and their interactions are governed by the principles of quantum mechanics. By replacing point-like particles with extended objects, strings, string theory smooths out the mathematical inconsistencies that arise when gravity and quantum mechanics collide. The vibrations of these strings can give rise to all the known particles and forces, including gravity, electromagnetism, and the strong and weak nuclear forces. This unification of forces is one of the most appealing aspects of string theory. The vibrations of these strings, governed by the laws of quantum mechanics, naturally give rise to the force of gravity, unifying it with the other fundamental forces in a single, consistent framework. This means that string theory has the potential to provide a complete and unified description of all the fundamental forces and particles in the universe. This unification has profound implications for our understanding of the universe's origins. According to string theory, the universe began not with a singularity, an infinitely dense point, but with a hot, dense soup of strings. This idea challenges the traditional Big Bang model and offers a new perspective on the birth of the universe. String theory suggests that the universe began not with a singularity, an infinitely dense point, but with a hot, dense soup of strings. As these strings interacted and vibrated, they gave rise to the particles and forces that we observe today. This idea provides a new way to think about the initial conditions of the universe and the processes that led to its current state. As the universe expanded and cooled, these strings coalesced into the particles that make up our world today. This process of coalescence and cooling is thought to have occurred in the first few moments after the Big Bang, leading to the formation of the familiar particles and forces that govern the universe. String theory thus provides a comprehensive framework for understanding the fundamental nature of reality, from the smallest particles to the largest cosmic structures. Perhaps the most mind-bending aspect of string theory is its prediction of extra spatial dimensions beyond the familiar three we experience in our everyday lives. While this concept might seem like something out of science fiction, it arises naturally from the mathematics of string theory, making it a fascinating subject of study. To visualize these extra dimensions, imagine a tightrope walker moving along a cable, carefully balancing with each step. From a distance, the tightrope appears one-dimensional, a straight line stretching across the landscape. However, an ant crawling on the cable experiences an additional dimension, the circumference of the cable, which is hidden from our distant view. Similarly, string theory suggests that our three-dimensional universe might be embedded in a higher dimensional space, with the extra dimensions curled up too small to be detected by our current instruments. These extra dimensions are not merely mathematical curiosities. They play a crucial role in determining the properties of strings and the particles they create, influencing our understanding of the universe. The size and shape of these hidden dimensions influence the vibrational patterns of strings, which in turn determine the masses and charges of particles, shaping the fundamental nature of reality.